Welcome to Chapter 8 on the other terrestrial planets, where we will go into the other planets before the asteroid belts and before the gas giants and the ice giants, which includes Venus, Mercury, and Mars. The closest planet to the Sun, Mercury is a truly inhospitable world of temperature extremes. Its extremely thin atmosphere and weak magnetic field leaves it virtually unprotected from countless impacts and a continuous bath of deadly solar radiation. Despite having a surface nearly as dark as coal, Mercury sometimes appears as one of the brightest objects in our sky due to its proximity to the Sun. We can see it from Earth only for a few hours before sunrise or a few hours after sunset because its angle from the Sun, its elongation, is always small. Because its orbit around the Sun is so elliptical, Mercury's maximum elongation ranges between 18 and 28 degrees. Here are some of the vital statistics to peruse at your leisure, and some of which we are going to go over in the following slides. The most impressive feature discovered by Mariner 10 is a huge circular region called Caloris Basin. This name derives from caloris, Latin for heat, and is in fact this feature that is the closest part of Mercury to the Sun as the planet's perihelion, closest approach to the Sun. Caloris Basin measures 1,550 kilometers in diameter, meaning that it has nearly 3 times the area as Texas. When viewed along the terminator, the border between day and night, where the shadows are longest and details clearest, the basin is seen to be surrounded by a 2-kilometer high ring of mountains, beyond which are relatively smooth plains. Caloris Basin was probably gouged out by an impact of an asteroid that penetrated the planet's crust. Messenger reveals that small impact craters inside the Caloris Basin that have been filled in by lava from volcanoes that were active long after both the basin and those craters were formed. A giant volcano 95 kilometers in diameter, bigger than the state of Delaware, has been seen in the basin. The Caloris impact was a tumultuous event that shook the entire planet. Indeed, the collision affected the side of Mercury directly opposite of the Caloris Basin. That area has a jumbled hilly surface covered nearly 500,000 square kilometers, about twice the size of Wyoming. The hills, which appear as tiny wrinkles that cover most of the photograph, are about 5 to 10 kilometers wide and between 100 and 1,800 meters high. Geologists believe that energy from the Caloris impact travels through the planet and became focused, like light through a lens. As it passed through Mercury, as this concentrated energy reached the far side of the planet, jumbled hills were pushed up. A similar pair of phenomena was to Caloris, and the jumbled terrain on the other side of Mercury can be seen on our moons Mare Orientale and chaotic hills on the opposite side of that world. Finding such a similar pair of phenomena on different worlds supports the connection between the impact and the jumbled surface. Looking at Mercury in more detail, we start to see a variety of differences from the features of the Moon. Unlike our moons Maria, Mercury lacks extensive craterless regions. Instead, Mercury has broad plains dotted with relatively small craters. Such plains are not found on the Moon. As we learned in section 7.5, the lunar Maria were likely produced by extensive lava flows from Rie valleys, flows that occurred between 3.1 and 3.8 billion years ago. The reason Mercury has no Maria analogous to those on our Moon is likely because Mercury has no extensive low-lying region to be filled with lava as occurred on our Moon. Dormant volcanoes were discovered on Mercury in 2008 by the Messenger spacecraft. Some of the materials creating the Mercurian plains came from such volcanoes, while the rest came through craters created as large as meteorites punched through the planet's thin, newly formed crust, allowing lava to well up from the molten interior to flood low-lying areas. The existence of craters on Mercury's plains suggests that these features formed just over 3.8 billion years ago. Near the end of the late heavy bombardment, Mercury's plains are therefore older than most of the lunar Maria, leaving more time for cratering to occur on Mercury. To date, 40% of Mercury's surface is covered by these plains, while the rest is more heavily cratered. Mariners 10 and Messenger also revealed numerous long cliffs called scarps meandering across Mercury's surface. Recall that they have also been observed on our Moon. Scarps are believed to have developed as Mercury cold. Almost everything that cools also contracts, water being a notable exception. Therefore, as Mercury's mantle and molten iron core cooled and contracted, its surface moved inward an estimated 11 kilometers since its surface first solidified. More than 30 ridges and scarp have been identified on Mercury's, ranging from length between 9 and 900 kilometers. Because it was already solid, Mercury's crust could not collapse uniformly. Instead, the crust wrinkled as it contracted, forming the scarps. These features and the lack of recent volcanic activity suggest that the planet's interior is solid to a significant depth. Otherwise, lava would have leaked out as the scarps formed. Because Mercury is less dense than Earth, you might conclude that Mercury has a lower percentage of iron, a common heavy element, than does our planet. Indeed, Messenger revealed that Mercury's surface has a low iron content. However, in terms of the percentage of its total mass that is iron, Mercury is the most iron-rich planet in the solar system. Only Earth's greater mass, pressing inward and thereby compressing our planet's inner parts, make it denser than Mercury. Figure 8.8 shows a scale drawing of Mercury's interior where an iron core contains nearly 60% of the planet's mass and 75% of its radius. Surrounding the core is a 600-kilometer thick rocky mantle. For comparison, Earth's iron core contains only 32.5% of Earth's mass and extends out to only 90 or 55% of our planet's radius. Mariner 10 also discovered that Mercury has a magnetic field of about as strong as that of Earth. However, since it is closer to the Sun, that does mean that there is a lot more solar wind to bombard it than there is on our Earth, and therefore it is going to be bombarded more by solar wind and be more inhospitable, as said earlier. Mercury is so close to the Sun, average separation of 0.387 U, or astronomical units, the average distance from the Earth to the Sun, that the Sun's gravitational force on Mercury's tidal bulges changed the planet's rotation rate before its surface solidified, with the two regions of high tide now locked into place on the planet. However, Mercury's highly eccentric E equals 0.21 orbit prevented the planet from being locked into synchronous orbit like our moon. Instead, Mercury developed what is called 3-to-2 spin-orbit coupling. The coupling means that Mercury undergoes 3 sidereal rotations measured with respect to the distant stars, not the Sun, while undergoing 2 revolutions around the Sun, as seen here. Mercury's mass is only 5.5% of that of Earth. Like our moon, the force of gravity is too weak on Mercury to hold a permanent atmosphere, but trace amounts of at least 8 different gases, hydrogen, helium, sodium, calcium, magnesium, potassium, argon, and oxygen, have been detected around Mercury. These gases are at least 10 to the 17th times less dense than the air we breathe. Scientists think the Sun is the source of the hydrogen and helium gas near Mercury, while sodium, magnesium, calcium, argon, and potassium gas escape from rocks inside the planet, a process called outgassing, which also occurs on Earth, and was a very difficult process to deal with when I was working with vacuum chambers, where the gases inside of the chambers would be caused by you putting the wrong type of material in there. If you put anything other than stainless steel in there or certain types of materials, then they would just gas out and make it so that the inside of your chamber where you were taking measurements did not have a good vacuum, was very gassy because of the materials that made it up. Let us move on to Venus now, the second planet from the Sun. One of the few things that Mercury and Venus have in common is that neither has a moon. Venus and Earth, on the other hand, have much in common. They have almost the same mass, the same diameter, and the same average density. Indeed, if Venus were located at the same distance from the Sun as its Earth, then it too might well have evolved life. However, Venus is 30% closer to the Sun than Earth, and this is one difference between the two planets leads to a host of others, making Venus inhospitable to life. At nearly twice the distance from the Sun as Mercury, Venus is often easy to view without interference from the Sun's glare. At its greatest western elongation, Venus is seen high above the western horizon after sunset, where, like Mercury, it is often called the evening star. Conversely, high in the eastern sky before sunrise, it is called the morning star. The maximum elongation of Venus is always between 45 and 47 degrees. Unlike Mercury, Venus is intrinsically bright because it is completely surrounded by light-color, highly reflective clouds. Because visible light telescopes cannot penetrate this thick, unbroken layer of clouds, we did not even know how fast Venus rotates until 1962. In the 1960s, however, both the United States and the former Soviet Union began sending probes there. The Americans sent fragile, lightweight spacecraft into orbit near the planet. The Soviets, who had more powerful rockets, sent more durable spacecraft directly into the Venusian atmosphere. And again, the book gives us a page of vital statistics, which we are going to go over in more depth soon. Building spacecraft whose technology could survive the descent into Venus's atmosphere proved to be more frustrating than anyone had expected. Finally, in 1970, the Soviet probe Venera, Russian for Venus 7, managed to transmit data for 23 minutes directly from the Venusian surface. Soviet missions continued until 1985, measuring a surface temperature of 750 Kelvin, or 900 Fahrenheit, and a surface air pressure of 92 atm, or 92 times the atmospheric pressure of Earth at sea level. Among other things, its temperature is higher than the hottest that Mercury ever gets, and this pressure is what you would feel if you were swimming 0.82 kilometers underwater on Earth. In contrast to Earth's present nitrogen and oxygen-rich atmosphere, Venus's thick atmosphere is 96% carbon dioxide, with the remaining 4% mostly nitrogen. This atmosphere is remarkably similar to Earth's early carbon dioxide-rich atmosphere. These gases were vented from inside Venus through volcanoes and other openings. Unlike Earth, however, Venus has no liquid oceans to dissolve the carbon monoxide and no living organisms to convert it into oxygen and carbon compounds, so it remains in the atmosphere today. Soviet spacecraft also discovered that Venus's clouds are confined to a layer that is 20 kilometers thick and located 48 to 68 kilometers above the planet's surface. Above and below the clouds are layers of haze which are also about 20 kilometers thick. Beneath the lower level of haze, the Venusian atmosphere is clear all the way down to the surface. Unlike the clouds on Earth, which appear white from above, the cloud tops of Venus appear yellowish or yellow-orange to the human eye. These colors are typical of sulfur and its compounds. Indeed, spacecraft found substantial amounts of sulfur dust in Venus's upper atmosphere and sulfur dioxide and hydrogen sulfide at lower elevations. The clouds themselves are composed of droplets of concentrated sulfuric acid. Because of the tremendous atmospheric pressure at Venus's surface, the droplets remain suspended as a thick mist rather than falling as rain. Standing on the surface of Venus, you would experience a perpetually cloudy yellow day, as seen here. All of the major chemical compounds spewing into our air by Earth's volcanoes have been detected in Venus's atmosphere. Among these molecules are large quantities of sulfur compounds that are observed to vary in concentration. Because many of these substances are very short-lived, they must be constantly replenished. These data suggest that sulfurous compounds in Earth's atmosphere come from active volcanoes. This idea is supported by the discovery in 2007 of lightning on Venus. Lightning has many sources in the atmosphere, including active volcanoes, as seen here on Earth when Eyjafjallajökull volcanoes erupted in 2010 in Iceland. The lightning on Venus, caused by the electrical discharge in the atmosphere, created short-lived magnetic fields that were detected by the European Space Agency's Venus Express satellite, further supported by the belief that Venus has active volcanoes came in 2015 when the Venus Express discovered regions of the planet's surface had suddenly heated up and were in the process of cooling. These hotspots were detected in rift valleys, which, as on Earth, are regions where lava can leak out from a planet's interior. At first, no one could believe reports that the surface temperature on Venus was higher than the surface temperature on Mercury, which, after all, is much closer to the Sun. Setting aside this initial skepticism, astronomers found a straightforward explanation: the greenhouse effect. The entire Venusian surface was mapped by the Magellan spacecraft, which arrived in Venus in 1990. While in orbit about the planet, Magellan sent radar signals through the clouds surrounding Venus. Like radar used by the police, some of the radar signals bounce off Venus and return to the spacecraft. By measuring the time delay of the radar echoes, scientists determined that the heights and depths of Venus's hills and valleys. As a result, astronomers have been able to construct a three-dimensional map of the planet. The detail or resolution visible on this map is about 75 meters. You could see a football stadium on Venus if there were any. Venus is relatively flat compared to Earth. More of Venus's surface is covered with volcanic plains and gently rolling hills created by numerous lava flow. Global radar images revealed that just two large highlands or continents rising above the general level surface of the planet. The continent at high levels in the northern hemisphere is called Ishtar Terra, after the Babylonian goddess of love, and is approximately the same size as Australia. Ishtar Terra is dominated by a high plateau, Lakshmi Planum, ringed by towering mountains. The highest mountain is Maxwell Montes, whose summit rises to an altitude of 11 kilometers above the average surface. For comparison, Mount Everest on Earth rises to 9 kilometers above sea level. The larger Venusian continent, Aphrodite Terra, named after the Greek counterpart of the Roman goddess Venus, is a belt of highlands that straddles the equator. Aphrodite Terra is 16,000 kilometers in length and 2,000 kilometers wide, giving it an area about one-half that of Africa. The global view of the surface of Venus shows that most of Aphrodite Terra is covered by vast networks of faults and fractures. Without weather or tectonic plates moving relative to each other, how can the craters be erased? Because there are few craters on Venus. Several mechanisms to explain this are being explored. Most theories posit that the lack of surface motion has forced Venus's crust to become thicker than Earth's crust. In one theory, heat from radioactive elements inside the planet causes mantle correction without tectonic plate motion. The temperature inside the planet eventually becomes high enough that the regions of rising mantle to create massive volcanoes out of which pour enormous amounts of magma that cover large areas of the surface. A variation of this theory proposes that the thickening crust is suddenly thinned from below by the horizontal convection motion of the mantle. Like stripping layers off of plywood, when so thinned, heat is able to rise above the crust and cause many volcanoes to form. Another theory proposes that, episodically, the one-plate surface of Venus is heated enough from below to crack and begin Earth-like tectonic plate motion until it cools down and again becomes a single plate. During this period of plate motion, this surface is erased and replaced. In yet another theory, the mantle becomes so hot that large sections of the crust melt more or less simultaneously, destroying the old crust and its craters. Indeed, this theory has been expanded to periodic global meltdowns occurring every 700 million years or so. For all of these models, when enough heat is released from the planet's interior, its surface once again solidifies. With the possible exception of local volcanic activity, the crust re-thickens. A day on Venus is more unusual than just being longer than ours. Unlike Earth and Mercury, Venus exhibits retrograde rotation, in which the direction of Venus's orbit around the Sun, counterclockwise as seen from space far above Earth's North Pole, is opposite the direction of its rotation, clockwise as seen from the same vantage point. In other words, sunrise on Venus occurs in the west and sunset in the east. Venus's rotation axis is tilted more than 177 degrees compared to Earth's 23.5 degree tilt. Because Venus's axis is within 3 degrees of being perpendicular to the plane of its orbit around the Sun, the planet has no seasons. Although we do not know what causes Venus's retrograde rotation, one likely explanation is that a monumental impact flipped the rotation axis early in the planet's existence. Mars. Mars is the fourth planet of the solar system and is the first planet past Earth. So the distinctive rose-colored hue of Mars makes it stand out in the night sky. For centuries, Mars has generated more excitement as a possible home for alien life than any other world in our solar system. This idea arose following the first well-documented telescopic observations of Mars in 1659 by the Dutch physicist Christian Huygens. Huygens identified a prominent dark surface feature that reemerged about every 24 hours, suggesting correctly a rate of rotation similar to that of Earth. Here again are Mars's vital statistics, which we are going to get through in more detail as we go through the chapter. Belief that advanced life existed on Mars skyrocketed at the end of the 19th century after Giovanni Virginio Schiaparelli, an Italian astronomer, reported in 1877 seeing 40 lines crisscrossing the Martian surface. He called these dark features canali, an Italian term meaning channels. It was soon mistranslated into English as canal, implying the existence of Mars of intelligent creatures capable of engineering feats. The speculation led Percival Lowell, scion of wealthy Boston family, to finance a major new observatory near Flagstaff, Arizona. By the end of the 19th century, Lowell had allegedly observed 160 Martian canals. By the beginning of the 20th century, it was fashionable to speculate that the Martian canals formed an enormous planet-wide irrigation network to transport water from melting polar ice caps to vegetation near the equator. In view of the planet's reddish desert-like surface, Mars was thought to be a dying planet whose inhabitants must go to great lengths to irrigate their farmlands. No doubt the Martians would readily abandon their arid ancestral homeland and invade Earth for its abundant resources, an ideal brought to life in 1898 by H.G. Wells in War of the Worlds. Ironically, we now have on the surface of Mars a spacecraft, the Curiosity rover, which is zapping that planet's surface with a laser reminiscent of the death rays depicted in the Wells story. The laser has zapped Mars' surface over 100,000 times, vaporizing small amounts of it, and a spectroscope on Curiosity analyzes the chemical composition of the released gases. Among other things that this rover has detected are glassy particles containing about water. These particles were created during meteor impacts, which heated and melted rock at the impact sites, enabling the glass to form. Also found are crystals created in volcanic rocks and chlorine-based chemicals such as perchlorate. And here we see Lowell's map of the different canals, which he viewed through his telescope in Flagstaff. As noted, Mars has only about 11% of the mass and half the diameter of Earth. While Mercury's small size and mass are attributed to a major collision when the planet was young, it appears that Mars is a relatively small planet because Jupiter swept up much of the mass that would have gone to Mars. Spacecraft journeying to Mars have sent back pictures since the 1970s. They show that Mars' surface is completely dry and that it has broad plains, shallow craters, enormous inactive volcanoes, and vast canyons. The broad northern plain is called Vastus Borealis, Latin for northern waste or northern devastation, and is shown in blue on the figure to the left. This plain is some 5 kilometers below the much more heavily centered and hilly plains in the south called the Southern Highlands. The causes of the significant differences in height of the two hemispheres is not known, but it may stem from either early tectonic activity or from a powerful early impact. Between the two hemispheres, Mariner 9 discovered a vast canyon now called Valles Marineris, which runs through roughly parallel to the Martian equator. Valles Marineris stretches over 4,000 kilometers, about one-fifth of the circumference of Mars. If this canyon were located on Earth, it would nearly stretch from New York to Los Angeles. The individual canyons that make up Valles Marineris are up to 8 kilometers deep and 200 kilometers wide. Valles Marineris begins with heavily fractured terrain in the west and ends with an ancient crater terrain in the east. Geologists believe that the western part of Valles Marineris was created by tectonic plate motion on the young Mars. Data taken between 1999 and today reveals magnetic plates locked into parts of Mars' surfaces in just the same way that separating tectonic plates lock magnetic fields into Earth rocks and boundaries between Earth's tectonic plates. Some of the eastern parts of Valles Marineris appear to have been formed almost entirely by water flow, similar to Earth's Grand Canyon, which is 9 times shorter and 4 times less steep than Valles Marineris. Although remote observations, such as those made by Mariner and other spacecrafts, have strongly suggested that water has long existed on Mars. The chemical verification of water there in the form of ice was first made in 2008 by the Phoenix Mars lander. In 2013, the Curiosity rover analyzed the soil samples and determined that they contain water. Most impact craters are located in Mars's southern hemisphere. This suggests that the Vastistus borealis has been resurfaced by some process that eradicated ancient lowland craters, consistent with either of the earlier explanations of the difference in hemispheres. Most of the volcanoes on Mars are located in the northern hemisphere. The largest volcano in the solar system, Olympus Mons, covers an area as big as the state of Missouri and rises 26 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. The highest volcano on Earth, Mauna Loa in the Hawaiian Islands, has a summit of only 17 kilometers above the ocean floor. Olympus Mons is a shield volcano, meaning that the lava pours down its sides rather than it being violently ejected. The flow is evident in the inset in figure 830A. While we do not know the active history of Olympus Mons, it is as high as it is in part because the lower gravity of Mars allowed the surface that issued from its flow downhill more slowly than occurs on Earth. The lava solidifies before it has spread out as much as occurs on Earth's shield volcanoes, therefore building up thicker layers in a taller volcano than the same flow would have created on Earth. While most of the volcanoes on Mars have high mounds of central craters, astronomers have identified the remnants of supervolcanoes on Mars. These volcanoes are so explosive that all that remains after they have been active is a flat crater filled with remnant lava. If the Eden Patera crater were an impact crater, it should have a high uniformly circular rim, possibly a central peak, and an ejecta blanket, none of which are true. Astronomers have discovered impact craters on Mars that formed in the past few years. In one case, an image showed no craters, while an image taken 67 days later in the same area reveals a cluster of new small craters. Careful study of these new craters shows that they uncovered ice that had been buried only a meter or two under the planet's surface before the meteorite struck. Based on the number of new craters found, astronomers calculated that about 200 new craters at least 3.9 meters in diameter are created every year on the red planet. Put another way, every area the size of Texas receives a new crater each year. Part of the Valles Marineris was apparently formed when large regions of Mars' surface moved apart due to tectonic plate motion. This activity is generated by the flow of rock under the planet's surface. However, there is no evidence that plate tectonic activity occurs on Mars today. This lack of activity indicates that more of Mars' interior is cold solid rock than exists inside Earth. This conclusion is supported by the observation that Mars lacks a global magnetic field. However, observations made in 2003 revealed that the sun creates tiny tides less than a centimeter on the solid body of Mars. As the land rises and sinks ever so slightly through the day, friction created by this motion in the planet's interior may provide enough heat to keep some of the interior molten. Although a global magnetic field on Mars is absent today, there are remnants of such a field. In 1997, the Mars Global Surveyor, which operated until 2006, discovered patterns of local regions of magnetic fields in a variety of places on Mars, similar to regions on Earth where tectonic plates separate and lock Earth's magnetic field in the rock. Geologists propose that when Mars was young, the internal dynamo created a strong magnetic field and that tectonic plates helped craft its surface. However, locking traces of its changed magnetic field in the then vanished rock. However, the planet quickly cooled. Its global magnetic field vanished and the tectonic plates activity apparently ceased nearly 4 billion years ago. As we will see in Chapter 11, the Sun has a magnetic field, some of which is carried far from our star by the particles of the solar wind. In 2017, astronomers discovered that this magnetic field interacts with the remnants of Mars' magnetic field. As a result, Mars has a magnetic tail pointing away from the Sun. Aurorae have been observed in Mars' atmosphere. Earth's aurorae result from charged particles trapped in the Van Allen belts, leaking earthward and causing electrons in the gases of our atmosphere to move to higher energy states, and then return to lower energy to emit photons, as discussed in section 4, or in chapter 4. These photons are our aurorae. Mars lacks a global magnetic field and hence lacks the equivalent of Van Allen belts. The aurorae there are caused by impacts from solar wind particles striking atoms and molecules on Mars' surface. Also, unlike our aurorae, which can last for hours, aurorae on Mars last only for a few seconds. A more molten interior early on in its existence is also consistent with the enormous volcanoes that exist on Mars. As noted earlier, most of the volcanoes on Mars are shield volcanoes, like the ones that created the Hawaiian Islands here on Earth. Such volcanoes are very different from stratovolcanoes such as Mount Fuji in Japan or Mount Etna in Sicily, where the material from inside Earth is ejected violently. The Hawaiian Islands are one of the most recent additions to a long chain of islands created by the growth of shield volcanoes rising through the Earth's crust under the Pacific Ocean. These volcanoes resulted from the hotspot volcanism process in which molten rock rises to the surface from a fixed hot region far below. The Pacific tectonic plates is slowly moving northwest at a rate of several centimeters per year. As a result, new volcanoes are created above the hotspot, while older ones move off and become extinct, eventually disappearing beneath the ocean. Because Mars' surface is apparently frozen in place due to the lack of tectonic plate motion, a hotspot can keep pumping lava upward through the same vent for millions of years. One result is Olympus Mons, a single giant volcano rather than a large change of smaller ones. This volcano summit has collapsed to form a volcanic crater called a caldera, large enough to contain the state of Rhode Island. Because Mars' solid crust and mantle, the region directly beneath the surface, are now so thick they insulate the surface, preventing any more molten rock from escaping. Therefore, we do not expect to see any more large-scale volcanic activity there. But we do see this nice magnetic field map that is local magnetic fields rather than global magnetic field. The Martian crust, the outer part of its solid structure, is at least 40 kilometers thick under the Vastus Borealis and 70 kilometers thick under the southern highlands. However, the boundary between thin and thick crust does not line up with the boundary between high and low terrain. Current models of Mars suggest that it has a core of about 34,000 kilometers in diameter, and that at least some of its core is molten. A detailed understanding of Mars' interior awaits the placing of seismic detectors on the planet's surface. To understand more about the activity on Mars' surface, we must examine its atmosphere, which today has only 0.6% of the pressure of Earth's atmosphere. As on Venus, some 95% of Mars' thin atmosphere is comprised of carbon dioxide. The remaining 5% consists of nitrogen, argon, water vapor, and traces of oxygen. Unlike the gravitational attraction of tiny Mercury, which is too weak to hold any of the gases as a permanent atmosphere, Mars' gravitational force is just strong enough to prevent carbon dioxide, nitrogen, argon, and oxygen from evaporating into space, but not strong enough to hold down water vapor. A growing body of evidence indicates that there was once a vast water-filled ocean in the northern hemisphere of Mars with more water than our Atlantic Ocean and smaller bodies of water in numerous places over the entire planet. Evidence for the ocean includes layers of rock deposited by water and channels in which water from the south flowed northward. Observations made in 2008 suggest that large quantities of liquid water existed on the surface of Mars for 2.5 billion years. In other words, until about 2 billion years ago, one of the factors that would have enabled the oceans to exist as long as they did was that Mars is believed to have a much thicker atmosphere in the past. More air above it makes it harder for liquid water to evaporate. That atmosphere would have decreased in density for several reasons, including some gases in the atmosphere being heated enough to fly into space, some air molecules in the upper atmosphere being broken apart by ultraviolet radiation from the sun and then drifting into space, and some gases freezing and then buried on the surface. Observation by the NASA spacecraft Mars Atmospheric and Volatile Evolution, MAVEN, has revealed that the solar winds is stripping off about 100 grams of Martian atmosphere every second. While that is a tiny amount, over billions of years it has led to a serious depletion of the Martian atmosphere. Eventually, much of Mars' surface Water evaporates and is drifted into space, never to return. Today, the concentration of water vapor in Mars's atmosphere is 30 times lower than it is in Earth's air. If all the water vapor could somehow be squeezed out of the Martian atmosphere, it would not fill even one of the Great Lakes of North America. This remainder of the water that was on Mars's surface has returned to ice, much of which remains there today. Most of that water has been covered with finely powdered, wind-blown regolith, which is why we do not see frozen lakes or similar features. Despite the low density of Mars's air, the red planet experiences Earth-like seasons because of a striking coincidence, first noted in the late 1700s by the German-born English astronomer William Herschel. Just as Earth's equatorial plane is tilted 23.5 degrees from the plane of its orbit, Mars's equator makes an angle of about 25 degrees from the plane of its orbit. If, as now is suspected, the northern hemisphere of Mars is lower than the southern hemisphere because the north was struck by a large body, that impact could have also tilted the planet and initiated the seasons there. The Martian seasons last nearly twice as long as Earth's because Mars takes nearly 2 years to orbit the Sun. When Mars is near opposition, even current telescopes for home use reveal its daily changes. Dark seasonal markings on the Martian surface can be seen to vary, and prominent polar caps of frozen carbon dioxide shrink noticeably during the summer and spring months. Unexpectedly, dust has been observed much higher than the dust photographs of Mars's atmosphere. Discovered by the MAVEN spacecraft, this high-altitude debris extends from 150 to 300 kilometers. There are a variety of plausible explanations for the source of this dust, including drifting upward from the lower regions of the atmosphere, debris released by the moons Phobos and Deimos, particles from the sun, and particles left behind by the passage of comets. The sky color also changes over periods of many years. In 1995, for example, the amount of dust was observed to have dropped dramatically compared to that observed in 1970s. The reason for such long-term changes is still under investigation. As on Earth, the temperature changes with the seasons on Mars. During the afternoons, heat from the planet's surface warms the air and sometimes creates whirlwinds called dust devils. A similar phenomenon occurs in dry or desert terrain on Earth. Martian dust devils reach altitudes of 12 kilometers. Spacecraft on Mars detect drops in atmospheric pressure as dust devils sweep past, just as on Earth. Many dust devils are large enough to be seen by orbiting spacecraft. In 2008, the Mars Reconnaissance Orbiter discovered buried glacier extending dozens of kilometers from mountains and cliffs. Remnants of a glacier have been seen in Grail craters. Surface water ice has also been detected. It is certain that much more water remains to be found inside Mars. Despite disproving the theory that Mars has broad canals or any other permanent liquid water, Mars-orbiting spacecrafts did reveal many dried-up riverbeds, river deltas, where water and debris emptied into lakes and oceans, dried lake beds, sedimentation laid down by water flow, and other water-related features. Some of the riverbeds include intricate branched patterns and delicate channels meandering among flat bottom craters. Rivers on Earth invariably follow similar winding courses, such as this. It also has two moons, Phobos and Deimos, Greek meaning fear and panic, but they are so small that they were not discovered until 1877 and look more like potatoes than the spherical moon that we have. In conclusion, there are many similarities between the terrestrial planets and many differences, and I hope that in this lecture that you have learned a few of the ways that they are similar, a few of the ways they are different, and a few of the ways that you can compare the two, or compare the four.